To estimate the worst-case kitchen load for an upscale golf resort, there are several factors to consider. This includes the occupancy of the guest rooms, potential walk-in customers, and the possibility of PGA banquets. A reasonable approach involves making certain assumptions and then performing load calculations based on those assumptions. Firstly, assume full occupancy of the 42 guest rooms, and consider double occupancy, which equates to 84 guests. Secondly, factor in a 50% walk-in customer potential, which is approximately 42 additional guests. Thirdly, account for PGA banquet potential of 200 guests. To estimate the load, calculate the number of meals served during breakfast, lunch, and dinner, and then add the load from the PGA banquet. For breakfast, if you have 84 hotel guests, estimate 3 meals per guest for a total of 252 meals. Project the walk-in breakfast at 126 meals, leading to a total breakfast load of 378 meals. For lunch, again, consider 84 hotel guests, estimating 3 meals per guest resulting in 252 meals. Project the walk-in lunch at 126 meals, resulting in a total lunch load of 378 meals. For dinner, use the same figures as before. This is 84 hotel guests, 3 meals per guest, equaling 252 meals. Project walk-in dinner at 126 meals, giving you a total dinner load of 378 meals. Now consider the PGA banquet. Assume a maximum banquet capacity of 200 guests. Assume a 3-course meal with hors d'oeuvres, which would be approximately 700 plate pulls. Finally, calculate the total worst-case kitchen load. If you sum up breakfast at 378 meals, lunch at 378 meals, dinner at 378 meals, and the PGA banquet at 700 plate pulls, the total is 1834 meals or plate pulls. Keep in mind some important notes. This estimate assumes a conservative 100% occupancy rate and maximum banquet attendance. The actual load will likely be lower, depending on occupancy and walk-in traffic. Always get more specific equipment information from the kitchen designer, once available, to refine the load calculations. Lastly, always allow for additional capacity for banquet preparation and storage. To further refine this estimation and ensure the electrical service is adequately sized, several detailed steps should be considered. Firstly, create an equipment list. Work closely with the kitchen designer to compile a comprehensive list of all kitchen equipment. This list should include everything from ovens and stoves to refrigerators, dishwashers, and smaller appliances like mixers and blenders. For each piece of equipment, note the manufacturer, model number, and most importantly, the electrical specifications. This information is usually found on the equipment's nameplate or in the manufacturer's documentation. Secondly, obtain the electrical specifications. For each piece of equipment, record the voltage, amperage, and power requirements, usually specified in watts or kilowatts. Pay close attention to whether the equipment requires single-phase or three-phase power. This will significantly impact the load calculation and the type of electrical service needed. If the equipment uses motors, note the horsepower and any specific starting requirements, as motors can draw significantly more current when starting up. Thirdly, calculate the connected load. Once you have the electrical specifications for all equipment, calculate the total connected load. This is simply the sum of all the individual equipment loads. Convert all power ratings to the same unit, typically kilowatts, to make calculations easier. For example, if an oven is rated at 5000 watts, that is 5 kilowatts. Be meticulous in this step, as any errors can lead to under or overestimating the total load. Fourthly, apply demand factors. The total connected load represents the absolute maximum power the kitchen could draw if every piece of equipment were operating at its peak simultaneously. In reality, this is unlikely to happen. Demand factors are used to account for the fact that not all equipment will be running at full capacity at the same time. Demand factors are typically expressed as a percentage and are based on the type of equipment and how it is used. Consult the National Electrical Code, NEC, specifically Article 220, for guidance on demand factors for commercial kitchens. For example, The NEC might allow a demand factor of 65% for cooking equipment if there are 4 or more units. Apply these demand factors to the appropriate equipment loads to calculate the actual demand load. Fifthly, calculate the feeder and service size. After applying demand factors, you will have a more realistic estimate of the kitchen's peak power demand. Use this demand load to calculate the required size of the electrical feeders and service. Feeders are the conductors that supply power to the kitchen from the main service panel, and the service is the main electrical connection to the building. The NEC provides tables, such as Table 310.15b16, that specify the ampacity of conductors based on their size and insulation type. Ensure that the conductors you select have sufficient ampacity to carry the calculated demand load continuously. Also, consider voltage drop, which can occur when electricity travels long distances through conductors. The NEC recommends limiting voltage drop to no more than 3% for feeders and 5% for branch circuits. If the voltage drop is excessive, you may need to increase the size of the conductors. Sixthly, determine the service size. The service size is the total capacity of the main electrical service to the building. This must be large enough to accommodate the kitchen load, as well as all other electrical loads in the building, such as lighting, HVAC, and other equipment. Perform a similar load calculation for the entire building, applying appropriate demand factors to each load. Sum the kitchen load and all other building loads to determine the total service size. Select a service size that meets or exceeds the total calculated load. Standard service sizes are typically available in increments of 100 amps, such as 200 amps, 300 amps, 400 amps, and so on. Seventhly, consider future expansion. It is always wise to plan for future expansion or changes in the kitchen. If there is a possibility that the kitchen will be expanded or that new equipment will be added, factor this into your load calculations. Adding an extra 20% to the calculated load can provide a buffer for future growth. This will help to avoid the need for costly upgrades to the electrical service later on. Eighthly, account for motor loads. Kitchens often have several pieces of equipment with motors, such as refrigerators, freezers, mixers, and ventilation fans. Motors can draw significantly more current when starting up than they do during normal operation. This inrush current, also known as locked rotor current, can be several times the normal running current. The NEC requires that you account for motor starting currents when sizing conductors and overcurrent protection devices. Use NEC Table 430.248 and 430.250 to determine the full load current for motors. Then, use NEC Section 430.52 to determine the appropriate size for the overcurrent protection device, such as a circuit breaker or fuse. Ninthly, specify overcurrent protection. Overcurrent protection devices are designed to protect electrical circuits from overloads and short circuits. These devices are essential for safety and preventing electrical fires. Select circuit breakers or fuses with an appropriate ampacity rating for each circuit. The ampacity rating should be based on the conductor size and the load it serves. The NEC provides detailed requirements for overcurrent protection in Article 240. Be sure to follow these requirements carefully to ensure that the electrical system is properly protected. Tenthly, consider power quality. Power quality refers to the stability and reliability of the electrical power supply. Poor power quality can cause equipment malfunction, damage, and downtime. Kitchens can be particularly susceptible to power quality problems due to the large number of electrical loads and the potential for harmonic distortion from nonlinear loads such as electronic ballasts and variable frequency drives. Consider installing power quality monitoring equipment to identify and address any power quality issues. This may involve installing harmonic filters, surge suppressors, or voltage regulators. 11thly, coordinate with the utility company. Before finalizing the electrical service design, coordinate with the local utility company. The utility company can provide information on the available service capacity, voltage levels, and any specific requirements or restrictions. They may also be able to provide assistance with load calculations and service sizing. It is important to ensure that the utility company can provide the necessary power to the building and that the electrical service is compatible with their system. 12th, documentation. Document all your calculations, assumptions, and design decisions. This documentation will be valuable for future reference, maintenance, and troubleshooting. Include a detailed equipment list, electrical specifications, load calculations, conductor sizes, overcurrent protection device ratings, and any other relevant information. Keep the documentation organized and readily accessible. 13th, professional review. Have a qualified electrical engineer review your electrical service design. An electrical engineer can verify your calculations, identify any potential problems, and ensure that the design meets all applicable codes and standards. A professional review can help to avoid costly mistakes and ensure the safety and reliability of the electrical system. 14th, grounding. Proper grounding is essential for electrical safety. Grounding provides a path for fault current to flow back to the source, which allows overcurrent protection devices to trip and to energize the circuit. The NEC provides detailed requirements for grounding in Article 250. Ensure that the electrical system is properly grounded in accordance with these requirements. This includes grounding the service equipment, grounding the electrical enclosures, and bonding all metal parts together. 15th, emergency power. Consider the need for emergency power in the kitchen. If the kitchen is critical for maintaining operations during a power outage, such as for food safety or patient care, consider installing an emergency power system. This may involve a generator or uninterruptible power supply (UPS). The emergency power system should be sized to provide power to essential equipment such as refrigerators, freezers, and critical cooking equipment. 16th, lighting loads. Don't forget to include lighting loads in your calculations. Kitchens typically have a significant amount of lighting, both general lighting and task lighting. Calculate the lighting load based on the square footage of the kitchen and the lighting levels required. Use energy-efficient lighting fixtures, such as LED, to reduce the overall power consumption. 17th, HVAC loads. Include the heating, ventilation, and air conditioning (HVAC) loads in your calculations. Kitchens often require significant HVAC capacity to maintain comfortable temperatures and remove heat and odors. Calculate the HVAC load based on the size of the kitchen, the amount of heat generated by equipment, and the local climate conditions. 18th, plumbing considerations. Coordinate with the plumbing contractor to ensure that the electrical and plumbing systems are compatible. Electrical equipment should be located away from water sources to prevent electrical shock hazards. Also, ensure that there is adequate space for electrical equipment and that it is accessible for maintenance. 19th, energy efficiency. Design the electrical system with energy efficiency in mind. Use energy-efficient equipment, lighting, and controls to reduce energy consumption and operating costs. Consider installing occupancy sensors to turn off lights when the kitchen is not in use. Also, consider using variable frequency drives, VFDs, to control the speed of motors and reduce energy consumption. 20th, compliance with codes and standards. Ensure that the electrical system complies with all applicable codes and standards, including the National Electrical Code, NEC, and local building codes. The NEC provides detailed requirements for electrical installations, and it is important to follow these requirements carefully to ensure safety and compliance. By following these detailed steps, you can develop a comprehensive and accurate electrical service design for the kitchen. This will help to ensure that the electrical system is safe, reliable, and efficient. Remember to work closely with the kitchen designer, electrical engineer, and other professionals to ensure that all aspects of the design are coordinated and that the final result meets the needs of the kitchen. Considering all of these aspects will provide a more robust and accurate estimate of the kitchen's electrical needs, ensuring the golf resort's operations run smoothly and safely.